let's talk a little bit about the past exam, problem 1, 2, 3. Okay. Should do it. Okay. Oops, that becomes orange now. That's fine. You guys see the problem? Okay. So that's what it is, right? I see. Okay. We've got the cantilever portion as well, like this. And then we have 3 point loads in the end, in the middle, and then another one at the cantilever. And the given shear force diagram looks, oh damn it, looks like this. Okay, so yeah. Without anything, you could see clearly that this one is missing, right? Because the shear force diagram show 0 value there, and therefore the correct shear force diagram would have to include some portion like that. Okay, and likewise, the bending moment diagram would go up a little bit more. Okay, and the given moment diagram is like this. So it should go slightly up like that. Whether or not it becomes positive, I don't remember. Okay, so this is what I've been missing. So the correct answer is that the mistake was done because this load was missing. That would be the correct answer. You know, I mentioned before that to say that shear force diagram and bending moment diagram are wrong is not the reason. Why are they wrong? That's the reason. And the reason why they're wrong is because the one who used the program forgot to put this load in. Okay. So let's go to problem number 2. I keep hitting the wrong button. Problem number 2, it's kind of a good challenge. B1, B2, and B3 is straightforward enough. So there's still quite 1 or 2 of you who could not even get the right tributary width. So, you know, if you could not really get that, you should consider, you know, dropping the class because you are in great danger. So B4, let's do B4. B4, we have the cantilever portion, right? So the beam looks like this, and then you have a series of B2 coming in. So you would have something like this, that, and that, correct? B4 and B4C would have to support B2, and then you have the self weight of B2. So this is your B4. Okay, and to consider B5, if you know, sit back for a minute and look at B5, you would see that B5 is actually B4 plus this. It's exactly B4 all over again, but with more load. So it's B4 plus this. Now you have B3 coming in here. And then you would have the floor coming in. Floor. So B5 is in fact B4 plus this one. All right, maybe I could say this is B3. Oh, sorry. That's B3. And then, yeah, for B4, this is B2, right? To draw the shear force and bending moment diagram for B5 may take a while, but then that's it. It's simple enough. Okay. Now let's move on to problem number 3. Problem number 3 is really straightforward. So, you know, maybe we don't have to talk about it, but anyway. Some of you still could not calculate the reaction, which is really a pity. And I have mentioned before that you should always take moment twice, because if you mess up the first one and then you use sigma Fy to calculate the vertical reactions, there is no helping. Okay, you pretty much done. Okay, so we have the say the uniform load here. And then that, and then that. Okay, I don't think that's any complication in that. I don't really remember exactly how we would end up, but for member number one, you should have something like this, right? The axial load, this, and then this reaction, and then you have the uniform load, and then you must have this one, and then that one. Okay, and that moment should be transferred to this member as well. So you'd have this, and then this. Okay, so that means because you have the presence of the moment coming in from this point load on the side, you would have this here. And the last one, so roller, so that's the, oops, that's a moment coming in, and that should counter with the moment produced by that load. Okay, and then you would also have the lateral load coming in here to make your sigma fx equal to 0, and then you have the vertical load coming in here, here, and here. So that's it, pretty straightforward. Okay. For those of you who get most of the things and don't get the full score, it's because you do not calculate the point of inflection. Okay, so then that's it for the exam. Is there any question about it?
For problem number 3, I confused about this. For my half, the bending moment, the recommend is the where. What half? I don't know.
Okay, you really want to discuss about it? It's fine, but let me. Wow, I don't want to share your exam, but there's no way I can look at it without you know, it being popped up on screen. Okay, so sorry. That's the one. Okay. Yeah, you got 7, right? That's your exam.
Yes, but I want to know what error or what mistake.
See,
was the bending moment.
You don't calculate the point of inflection. You did not. But that's a problem. That's a problem. You didn't calculate point of inflection. Okay. So for those of you who got 7, you should know now that you didn't calculate the point of inflection. That's why you got 7. Okay. And let's say that's enough. Okay. Here. In order to calculate the point of inflection, let's say I'm going to write this as V BC, okay, because most of you guys call this member BC, and then let's say this is MBC. This is the perhaps W1, right? So your moment equation would be to consider the downward force. First becomes minus MBC minus W1 X, right? Because we don't know where it is. And if now you have the conditions, because your X can fall in this region where you have the uniform load. So it's going to be X, let's say, but you must know that X is within the uniform load, okay? That's going to be x squared over 2, right? So if this is negative moment, then plus VBCX equal to 0. So you solve this, and if you get x less than this distance, it's correct. But you should be able to guess from your bending moment diagram that, you know, one point of inflection is within this, but another point is out of this region. So let's say this is x1, say x2, maybe it is better to write the moment equation from the right. So that becomes, let me call this CB, and then this is V CB. So that's pretty easy. For x2, that becomes minus MCB plus VCB multiplied by x equal to 0. So to clarify that, that's x2, that's x1, that's x1. You see, it's pretty easy. And you have done this before in the mechanics of materials class. I've seen your exam. Okay? If you do this, like 1 point each. Okay? Is there any question? Any more question? Oh, all quiet. So, well, if it's all quiet, let us begin the new topic then, okay? Generally, if you look at the handout, you see that the next chapter after the frame is the influence line, but I shuffle the order, and I would talk about the influence line last in the class because say that it's not very well, you know, continuous from what we have done before. Clear, right? Thanks a lot. Okay, so you guys can do it, but you don't do it. You didn't do it. Okay, let's go back to the new topic. So I move the calculation of deflection and calculation of the indeterminate structure forward. Okay, and I will finish with the influence line. Okay, so let me show you this problem. Let's see here. Hey, it's gone. Impossible. Huh? Actually, you know, because I really want to use that one, so just give me a minute. Okay, I thought it's in that bundle. It's not. I can easily do it by my you know. Okay. I took this from the mechanics of materials class. It's from the Singer textbook. I love it a lot. Okay, so you know it goes like this. Okay, this is a concept. So that is this beam. You guys see this, right? Like this. Okay, and that is this couple that is producing moment equal to 400 kilogram force meter. Okay, at the location 1.5 meter. And the beam is like 3 meters long. Okay, so now you can see that if you have a beam like this, it tends to, you know, create a rotation in your structure, right? And it will force your structure to come down. Correct? So the question is, if I am going to put this load, P, so that the deflection at the tip of this beam is 0, how much is P? So that delta at the tip is 0. So let's not do the calculation. Let us get the idea first. Okay? What would be the idea to solve this problem? Now, ladies and gentlemen, let me tell you one more thing. Generally, if this class was held on campus, many students would, ask a lot of questions about the concept, and we would spend the first session, repeating this. But if you guys stay quiet, and I am the only one who talks, I find it very hard to keep repeating myself. Okay, so your participation is important. Okay, so what would be the idea to solve this? Anyone? I want to know. Oops. So the sharing is gone, right? Can you see it?
Yes.
Still, still
Huh?
here.
No. Can you see my screen?
Yes.
Still see.
Strange, because
It's not gone.
it's not gone. So I am gonna draw a picture of a bird. Let's say a fish. So you can see it. That's my fish.
Freezing.
Can you see the fish?
Oh, it's freezing.
Yeah, that's what I thought. Let me erase the fish first. No fish. Okay. All right. Let us begin sharing again. It happens. Huh? Always Tuesday morning. Huh? Okay, it's back, right? No fish. So what would be the idea? If I want to know how much P it must be, so that the deflection at this particular point, this point, is 0. Delta here is 0. How much P do I need? How do I calculate that? Say, oh no, there's a big hole in my shirt. I'm going to count to 3, okay? 1, 2, 3. Okay, nobody answers. So the idea would be that the deflection caused by moment couple must be equal to deflection caused by P, right? Because the couple would bring the beam down, because it's this moment in this direction, right? So your beam will come down. So it's a downward displacement at the tip that this couple is causing. But when you look at the load P, the load P is clearly pushing up. So the load P is causing the upward deflection. So whatever the method you use, but when you use the method, any method to calculate the displacement by couple, it's a easier way to write plus the deflection caused by P must be equal to 0. So that becomes our condition. Okay, do you guys grasp the concept? Hello?
Yeah, yes.
I want to hear more than one person, please. What about the rest of you? Can
Get
you
it?
see what we are trying to do here? What I'm trying to do here? The couple will cause your, one second. My son forgot his straight edge around here, so it can be useful. If this is the support, the couple trying to bring the beam down, right? But we have the load P trying to bring it up. So when the two sets of load are applied at the same time, which I should say simultaneously, the couple is bringing it down, the load is pushing it up. So if we break it down and look at it from, you know, one load at a time, you will see that this downward displacement caused by a moment, if it is equal to the upward deflection caused by the load, in the end, when I combine them, the deflection at the tip of this beam will be 0. Right? Okay, kind of difficult. Similar to concept of superposition. Yes, sir. In fact, this is superposition. This is in fact superposition. So you okay with that, right? Let's say, let me give you the number, but I will not show you the calculation yet because I want you to get the concept first. So if I use the momentary method, I can calculate that the displacement by a couple is equal to, that's actually the bending moment diagram is and then look like this. And then I can use the moment area to calculate the, let's say that's point A, it's a TAB, okay, that's A, that's B. So that is going to give me minus 1350 over EI. Okay, if I focus on the load P, the bending moment diagram I have is going to be like that. Oops, that's a bad one, right? You should know right away. Moment diagram should be like this. Yeah. And that is a P multiplied by L, so it's a 3P. Okay, I again calculate TAB. I will get delta due to P in terms of P, and it is equal to 9P over EI. So if I put them in my superposition equation, yes, you're right. I like that you can see this. This is our superposition. Okay, I will now have 1350 over EI minus, oops, I'm sorry. This is minus, right? Plus 9P over EI equal to 0. So EI, they are gone. Now I can say that P must be equal to 150 kilogram force. That's my answer. Okay, you guys still with me?
Still ค่ะ
Okay. Thank you. Anyone? What about the rest? Hey, Junior. Apart from Napat, You know, anyone else? Come on, talk to me. If you are not with me, you want me to repeat, you must speak up. Don't be embarrassed. Nobody is going to say that you are stupid or anything. Okay, with me, that's another senior. Thanks a lot for your response. But what about you, junior? A senior and super senior, they have seen this before. So they know. They are here because they made stupid mistakes, silly mistakes. That's why they are here again. But for junior, you've seen this for the first time. I want your response. That's the end of it. Oh, okay, I still have more space. Hey.
Still here, huh?
Yeah, Nakarin, okay, you're with me?
Yes, huh?
Thanks a lot. What about let's you know what, Nakarin, because you respond to me. Okay, trying to understand. Thanks a lot. You want me to repeat anything? You must say now, Siddha. Nakarin, call one of your friends to explain this again.
อัครพันธ์ครับ
Akrapan, นะครับ Akrapan,
Yes.
this to your friends again. What's going on here?
Okay, we would like to consider a 2 point that you mentioned for the superposition method, right? The first one, the couple, that's the deformation occur from the couple and the middle will occur in this, the elastic curve that you draw it here, and it will show the negative value. And this one will be expressed from the equation that we have learned for the double integration. Area.
But let's not
Yeah.
let's not you know, focus on the calculation yet. Just focus on the concept.
Oh, okay. Like this that I mentioned.
You know, let me streamline it for you. How do we calculate P? Can you explain that? How do we obtain
P, right?
P? Yes, the pink P.
Yeah, for an area under the triangle, TP times the distance, right?
No. Okay, I think you probably understand. I don't want you to explain how we calculate it. I want you to explain how we obtain the P. Okay, that's fine. Akrapan, can you call the next person?
Okay, maybe Puvanan is good. Okay.
Yeah, Puvanan is good. Yeah, but Puvanan, the next time you must call a lady. Okay, Puvanan, are you here? Puvanan doesn't respond now. Akrapan.
Okay. Vishakon.
Vichakon, are you around? Huh? Vichakon is not around. Call someone. Avishakon, your name is here, but he does not respond. So okay, that's fine, because you have like, you want to call another name because you have 2 strikes now. It's going to be 3 strikes out. Just like baseball.
Okay. P off. Okay. P off Nopadon.
Off Nopadon, no. Let's call Junior. Nopadon has done.
Okay, sure. How we call I think Thanawat.
Thanawat เหรอครับ Thanawat has done okay in the exam, right? Thanawat.
Thanawat may go to toilet ครับ
Really? So Akrapan, your friends hate
I think today I'm no lucky.
you should think that your friends hate you. They give silent treatment. As soon as you call his name, he just goes to toilet.
Okay, I think you can pick someone. Yeah.
So no, I'm not going to pick anyone else because we are like 5 minutes. 5 minutes
sure.
break. So I have to assume that because nobody is responding to me, so I have to assume that, you know, everybody gets it. Okay. So listen carefully, guys. Listen carefully. Now, I am simply asking you, how much P do we need to maintain the displacement equal to 0 at the tip, right? But let's say if I change the perspective a little bit by saying instead of writing the load P, I am going to erase it. And now I am replacing the load P with the support roller. Do you think it is the same beam?
Yes, yes.
It is or it isn't?
It
is.
It is. So when I replace the load P with the roller in a way can represent the load P, correct? Because a roller support has one reaction, and it is exactly the vertical reaction. So I can easily replace the load P with the roller. Or in other words, instead of writing the beam just like that from the beginning, I can write the beam like this, right? And simply ask you to calculate the force P here, which instead we can now call it a reaction. Okay? And when we replace the load P by the roller, and we can call this a reaction. Now you look at the structure. How many reactions do we have for this entire structure? We now have 1, 2, 3, and 4. How many equilibrium equations do we generally have? We have 3 equilibrium equations. But now we have 4 unknown reactions. So that means we now have a situation where we have unknowns more than the equations we have. So that means we now have the indeterminate structure. Because you cannot determine the reactions straight away by using your equilibrium equations. The full name is statically indeterminate structure. That means you cannot determine the reactions by the method of statics anymore. And that means we need an extra equation. And I can simply say that the extra equation that we need is what we call degree of redundancy. R here, degree of redundancy is equal to the number of unknowns minus the number of equations that you have. And here it is 1. And this one is the degree of redundancy. That means you need to find an extra equation. To solve the structure. And that extra equation is this one. if you can establish this equation, you can solve for that, right? But in the beginning, instead of writing a support condition to you, I just ask how much this load P is. Okay? Let me continue for a minute or two. We now use displacement to solve the extra unknown that we have. And we use it such that we say these two displacements, when they add up, they must be equal to 0. So let me try and continue here. Displacement I can say sigma displacement maybe. When you add up, it must be equal to 0. So that's why somebody would call this consistent deformation. Okay, and the way that we solve the indeterminate structure by setting up this equation that has the 0 displacement becomes the method of consistent deformation. Okay, it becomes the method of consistent deformation. Okay, the sharing is now gone. So you know what? Let us take a break. And okay.